This is part 9, the final part of the rates and equilibrium topic. It's AQA GCSE chemistry and it's valid for dual and triple award students. As always, I'm going to say pause the video, try the activities for yourself. In this video, we're going to build on what we did last time and use the Chetaliers principle and look at the impact on equilibrium position where we are dealing with dynamic equilibrium. I am going to say being secure in your knowledge of what was in the previous video is really important if you're going to tackle what's in here. But we're going to focus on the effect of changing pressure and temperature on the position of equilibrium in reversible reactions. So when you're ready, have a think about some of these questions. So for the first question here, you need to remember what the Chetaliers principle is, that if a change is imposed on a system, the system will act to oppose that change. So if the pressure is increased, the system will try to decrease the pressure, opposing the change, as we've said. Let's consider a specific example, nitrogen and hydrogen reacting to make ammonia. What do we think would happen to the position of equilibrium if the overall pressure on the system were increased? Well, the first thing that we're going to look at here is that in the equation there are 4 moles on the left hand side, there are 2 moles on the right hand side. You can also think about that as being 4 molecules and 2 molecules. And let's draw what that would look like. If I had 100% reactants in a system of fixed volume, I would have 4 molecules. They would be colliding with the surface of the container, exerting a pressure. But if I had 100% products, I would only have 2 molecules, or 2 moles, half the amount. So they would be exerting half the pressure. The pressure in the box on the right-hand side is half the pressure on the left-hand side. If a pressure is increased, the system will try to decrease that pressure. For that reason, the equilibrium shifts to the right. And this is the important bit. This is the statement you need to remember and understand. Increasing pressure favours the reaction that leads to a decrease in the number of moles. So let's now think about some examples. In this case, what will happen if I decrease the pressure? Well, the system will act to oppose that change. It wants to increase the pressure. It's the same equation as before. There are 4 moles on the left and 2 moles on the right. So if I decrease the pressure, the equilibrium is going to shift this time to the left. It's going to favour the reaction that leads to an increase in the number of moles. The pressure has been decreased on the system, so the system will try to bring it back up by having more molecules to collide and exert that pressure. Let's look at another example. And in this case, we've got 2 moles on the left and 1 mole on the right. So for A, if I increase the pressure, the system will act to oppose that increase. So it's going to want to decrease. It's going to favour the reaction that leads to a decrease in the number of moles. Got 2 to 1. So the equilibrium will shift to the right. Now let's have a think about B, decreasing the pressure. Well, the system will act to oppose the decrease in pressure. So it's going to favour the reaction that leads to an increase in the number of moles, 1 to 2. The equilibrium is going to shift to the left. And another example here. And on this one, what's interesting is that there are 2 moles on both sides. Now that means there's a very specific opportunity to question you on this. If I increase or decrease the pressure, the system will act to oppose that change. But actually, it can't act to oppose that change by shifting equilibrium to the left or the right, because both sides have the same number of moles. Changing pressure will not lead to a change in equilibrium position if the number of moles on both sides is the same. Do be ready for that in the exam. So that's pressure. Now let's focus on temperature. This is the Haber process, nitrogen and hydrogen reacting to make ammonia. Have a think about the questions. When you're ready, move on. So the reaction above, the forward reaction, is exothermic. What impact will that have on the temperature of surroundings? And what you find in an exothermic reaction is heat energy is released to the surroundings, so the temperature of those surroundings and the temperature of that closed system in a reversible reaction will go up. So what assumption would we make about the reverse reaction? Well, if the forward reaction is exothermic, we are going to assume the backward reaction is endothermic. And actually, the energy change is the same in magnitude, but the forward is exothermic, negative. The backward is endothermic, positive. If you're not sure about those, it's useful to go back to the previous topic where that was discussed in much more detail. So we would expect the temperature of the surroundings to go down in the backward endothermic reaction. A few more questions now to link it to the Chetalier. If I were to decrease the temperature of the system, what will the system try to do? Well, it will seek to oppose that change. So it will try to increase it. And increasing will always favour the exothermic reaction, or decreasing temperature, will always favour the exothermic reaction, the one that will increase it back again. So what will that do to the position of equilibrium? Well, the forward reaction here is exothermic, so it's going to shift the equilibrium to the right, because forward is exo. And if it's shifting equilibrium to the right, what will that do to the yield of ammonia? It will increase the yield of ammonia because the equilibrium is closer to it. Again, that was discussed in quite a lot of detail in the previous video. Questions for you to have a go at. Try this. And once you've had a go, the equation, we've got H2O and carbon reacting to make H2 and CO. And actually, it's balanced already. We are told that this is forward reaction is endothermic. So what will happen if I increase the temperature? If I increase the temperature, the system will act to decrease the temperature. It will shift to the right to favour the endothermic reaction. What will that do to the yield of carbon monoxide and hydrogen? It will give us a greater yield. In industry, that would be really important because we want to make more products. What about if I were to decrease the temperature? Well, the system would want to increase the temperature, so it will shift equilibrium to the left, favouring the exothermic reaction, because if the forward is endo, the backward must be exo. And what will that do to the yield of carbon monoxide and hydrogen? It will decrease it. And we have another question for you to take a look at here. So the equation here, if you need it, and the forward reaction is exothermic, so if I increase the temperature, the equilibrium will shift to the left, favouring the endothermic reaction, and that will decrease the yield of ammonia. But if I decrease the temperature, the system will want to increase the temperature, so it will favour the exothermic reaction, shifting equilibrium to the right, and that will give us a larger yield of ammonia. This is a complex topic, and it is worthy of spending more time reviewing it again and again until you're confident that you can answer the sort of questions that you've faced in here. But that takes us to the end of this video and the end of this topic. Thank you for listening, and goodbye.